Hello, now we reach chapter 20. The topic is atomic spectroscopy. Okay, the name indicates many things actually. This method of analysis depending on the atomization of the sample, and then we measure the um, absorption or emission at specific wavelengths from the atoms. Okay, and basically this atomic spectroscopy is a destructive technique. Destruction means that the sample, original sample, is totally destroyed. Okay? You will see soon. Okay? The first example of this chapter is an anthropology puzzle. Okay, look at your the front page of chapter 20. Okay, and you see two spectra. Okay, that's the dentin analysis. The dentin is a part of your teeth. Okay, the above one is the modern tooth from uh, Krakow in Poland. Okay, and the low one is um, the same dentin sample, but from a tooth from Spitsbergen in Norway, about AD 100, 1800 AD. All right. You see a very big difference in the middle part. Okay, and actually you see many elements from teeth. Okay, silver, antimony, and what, iodine, and mercury, and lead, etc. But very surprisingly, the sample from people long time ago, not very long, more than about 200 years ago, right? Um, the person from uh, who lived in the Scandinavian the area, it shows very the all kinds of elements, especially rare earth elements, okay, in this middle region. Dyspronium, holmium, and I'm sorry, I don't know the orbium. What's the name for Tm? Ytterbium, yeah, like that, hafnium and ruthenium and tantalum. Yeah, and uh, the question is why spectra are so different. But before we ask such a question, then you have to be amazed that the the atomic spectroscopy can reveal such a difference. All right, yeah. And this one uh, after atomization, and then the each atom was analyzed by mass spectrometry. Okay, as you know, the y-axis is atomic mass, and y-axis is signal. You see, first samples are atomized completely at very high temperature, and then um, the individual, especially individual metal atoms are detected by mass spectrometry. Okay, so here is an overview of atomic spectroscopy. Okay? As I said, this is completely destructive technique. The samples are atomized, okay, and totally destroyed. And to atomize samples, you need very high temperature. Okay, samples are vaporized at these temperatures. Okay, at least 2000 K and up to 8000 Kelvin. All right. So at these high temperatures, samples are decomposed into atoms. Okay. may not be completely, but most of them are atomized. So these atomized samples are detected by emission and absorption of characteristic lambda of radiation. But here, you see, the detection method was mass spectrometry. Okay, so that means this atomic atomization, you know, that part is connected to mass spectrometry. Okay, but usually after atomization, we measure the emission, like that is called atomic emission spectroscopy (AES), or absorption atomic absorption spectroscopy (AAS), or you want to measure the fluorescence. Okay, here you'll see in detail. Okay, Mm. atomic fluorescence spectroscopy (AFS). All right. And what are characteristics of this technique? They are highly sensitive. Okay, very highly sensitive. You can detect. Let me see here. Part per trillion concentration can be detected. Okay, and second characteristic is simultaneously you can detect multi-element analysis. Although you see our textbook doesn't say much about that, I will maybe give you some complementary material, how we can perform multi-element analysis, which means that after atomization, okay, about 50 elements could be simultaneously analyzed. Okay, that's because each atoms have their own energy levels. Okay, electron energy levels, and those energy levels are well defined. So by checking, by observing the emission line, yeah, and then we can determine which elements are there or not. So modern instruments can provide the ability to analyze 50 elements at the same time. Okay, so it can be automated. Okay, automatical analysis of many samples with ease. Okay, so the analysis itself is not very difficult. Okay, it's easy. Okay, so now atomic spectroscopy is a principal tool of analysis in analytical chemistry. AS is a principal tool. Okay? So usually concentration range is ppm. Okay, or sometimes it may be down to ppb, okay, part per billion, or even down to ppt, part per trillion. Okay, and without a pre-concentration step. Okay, if concentration is quite low, then usual analysis requires pre-concentration, but it doesn't need to do that. Okay, so precision is typically 1 to 2%. Okay, this precision I think is good enough. And you can do the analysis of many samples using an auto sampler. Okay, so with an auto sampler you can run for many hours without human intervention. Okay, so that's why this one atomic spectrometer are widely used in analytical chemistry lab. Okay. Yeah, here is the this figure shows overall picture of atomic spectroscopy. Yeah? Atomic spectroscopy, actually there are three different techniques. First one is atomic emission spectroscopy. Okay, here look at that. This is flame, yeah? Very hot flame, whose temperature is in the range of 2,000 to 8,000 Kelvin. Okay, so samples are thrown into this flame from the bottom. Okay, since the temperature is very high, all the samples are destroyed and atomized. Okay, inorganic elements are all you know destroyed, and yeah, we can analyze those inorganic elements. Usually we can analyze the elements. Okay, so atomize the element, metal elements. Now you see in the in a in a very hot this condition. So each atom, each atom has very discrete electronic energy levels. Since the temperature is very high, so electrons in individual atoms now excited to excited states. Okay, and then naturally those electrons in excited electron states now transition to the ground state or lower energy states. Okay, and then it emits characteristic um, you know the light. Okay, characteristic electromagnetic radiation whose wavelength is well defined. Okay, and very sharp. That is called atomic emission. Okay, and then those electromagnetic radiations of different wavelengths now discriminated by the monochromator. Yeah? So in this case, monochromator, the resolution must be very very high, and and then it is detected. So by looking at the wavelengths, we can decide um, which elements are present in the sample. Okay, that's the atomic emission. Okay. Here samples is liquid sample is aspirated into flame. Liquid evaporation takes place. Yeah. And also solid could be atomized in flame. Okay, flame path length is about 10 centimeters long. Okay, you'll see soon. And atomic absorption spectroscopy, uh, you need to light source. Okay, let's say now you want to determine the concentration of ion in the sample. Okay, now ions containing samples are totally atomized, and in this flame you have ion atoms. Okay, and then rather than measuring the atomic emission, but you use hollow cathode lamp made of ion atoms. Okay, and here in ion atoms, since it contains ion atoms, it generates very specific light. Okay, whose wavelength is exactly same as the ion atoms in the flame. Okay, and then this electromagnetic radiation now is absorbed by ion atoms in the flame. Okay, and we measure this monochromator is the we tune this monochromator wavelength to the this atomic absorption wavelength of ion. Okay, then we detect the what the colored cathode lamp intensity after absorbed by this the ion sample ion atoms here. Okay, and uh, the other technique is called atomic fluorescence signal. Okay, here in this case laser beam usually is used. Okay, and then laser beam induces the electronic transition, and then it generates fluorescence, and this fluorescence is detected by detector. Okay, so you have to differentiate the difference between atomic emission spectroscopy and atomic fluorescence spectroscopy. Okay, here in atomic emission spectroscopy, you don't need any external light source like a laser. Okay, here it illustrates this one. This is in atomic emission. Okay, electrons are excited to the upper excited state, and then electrons are now make a transition down to the ground state here or there. Okay, and atomic absorption, you know, the absorbed, the absorbance is measured. Okay, the absorption is induced by this hollowed cathode lamp. Okay, in the meantime, atomic fluorescence transition is that transition to the upper electron state is the same as atomic emission, but now you measure the fluorescence, okay, from this state or this state. In that case, you need the usually a laser, okay, and atomic absorption of sharp lines from hollow cathode lamp. Yeah, that's the atomic absorption, and in atomic fluorescence spectroscopy, fluorescence following absorption of laser radiation. Okay, and for atomic emission spectroscopy, emission is from a thermally populated excited state. All right. Yeah, here is the schematic diagram of the this technique here. This is for the atomic absorption because it uses hollow cathode lamp. As I said, there are many hollow cathode lamp depending on elements. Okay, so if we want to measure the copper concentration, okay, in the sample, you have to use the hollow cathode lamp made of copper, okay, because that lamp now generate the light, which is characteristic of copper. Okay, anyway, light is from hollow cathode lamp now enters this flame. Okay, this flame is quite linear. Okay, the distance between here to there is about 10 centimeters. Okay, now samples are aspirated from here. Okay, and then it goes into this flame. Yeah, and but of course you have to provide air and fuel. Okay, depending on which fuel you need, or depending on maybe air and or oxygen. Okay? And then the flame temperature also depends, varies. Okay, anyway, so from here to there, and your samples are distributed in the flame and then atomized. And then the atoms of an element of your interest now absorb this P0, and then this one, the transmitting intensity is P. Okay, the other process is the same, and then is the wavelength is selected by this monochromator and then detected. All right. Here's an example. I'm sorry. Uh, Look at this one. So here you can measure the transmittance, but usually people measure absorbance. These equations are the same as ordinary optical spectroscopy. Okay, you measure absorbance. A equals minus log t. Okay. Here, the hollowed cathode lamp HCl, for example, if it is made of, if it is ion cathode, okay, when cathode is bombarded with, neon and argon ion beam, okay, and then this ion, elemental ion, you know, are excited, okay, and they evaporized and emit light, okay, and important is that this emitted light wavelength, with this wavelength is specific to an ion. Okay? So, unlike ion atoms in flame absorb this light, okay, and we measure this absorbance. Okay, so here difference between atomic and molecular spectroscopy. Molecular spectroscopy, you measure the molecular spectrum. Okay, since molecules are made of many atoms, okay? Usually the spectra are very broad. Okay, but the atomic spectroscopy, the spectral the width is very sharp. Okay, yeah, here for the liquid and the solid sample, this one, uh, the width of absorption, okay, is about 100 nanometers. Okay, this is very wide wavelength. But for gaseous sample, you know, usually the spectra are very sharp. Okay, here. So the big difference between atomic and molecular spectroscopies is that bandwidth. Okay, here this figure illustrates very nicely. Look at that. This is uh, emitted. Okay, the intensity. This is atomic emission spectra. Okay, this x-axis is wavelength. Yeah, you see the wavelengths. This is 300.4 and the 3, 300.2 and 300.1. You see how well these um, elements are resolved. Okay, here this width is less than about zero point 0.3 nanometers, but within this very narrow wavelengths you can see the, these elements, right? These spectra are very sharp. Okay, that's why this atomic emission spectroscopy is very sensitive, and we can dissolve, we can determine many elements. Probably 50 elements could be determined at the same time. Okay, so liquid and solid sample bandwidth is about 100 nanometers, but gaseous sample after atomization bandwidth is very narrow, 0.001 nanometers. Okay, that's why this was closely spaced. This spectra could be resolved, all right? But in order to resolve um, these spectral features, you have to have very good, yeah, uh, the monochromator with very high resolution. Okay, so more than 70, elements could be determined at the same time. All right. Atomic fluorescence spectroscopy. Here, atoms in flame are irradiated by laser. Okay, you know the difference between AFS and AES. Okay, so the atoms are excited to the excited state, and then it undergoes transition to the ground state and emit fluorescence. Okay, and fluorescence is more sensitive. How sensitive? 1,000 times than absorption. Okay, but it is not used in routine. Okay, and okay, here is an example. Yeah, this figure shows how atomic fluorescence spectroscopy is done. Okay, here is the capillary, and then in capillary, you here is the liquid drop, all right, and then this liquid drop on this liquid drop, you what shine, irradiate. This is a laser beam. Okay, now it is the 193 nanometer laser beam, and then here inside the liquid drop, the atoms are okay atomized. Okay. Oh, I'm sorry. In this case, atomization, vaporization is done by another laser from this side. Okay, then these liquid samples are vaporized, and then the the elements are excited by this laser beam. Okay, look at this wavelength is 190 nanometer wavelength. Okay, and then uh, atoms now generate the fluorescence. Okay, and then specific, okay, the fluorescence at a specific wavelength is detected. In this case, at 406 nanometers. This is characteristic, okay, of lead, okay, lead atom. And then this fluorescence intensity is detected by the detector, okay. This one here. So if the in this case lead atom concentration is higher, then you can see the stronger signal, okay. So this figure shows that the fluorescence intensity is linearly changing with respect to this lead ion concentration, okay. Look at this unit, and this is part per billion, okay, ppb. At any rate, this low concentration can be rather easily detected by atomic fluorescence spectroscopy. All right, and here look at that. This bandwidth. Okay, here is this is 1 nanometer, and so this bandwidth is less than 1 nanometer. Okay, so fluorescence is more sensitive than absorption because we can observe a weak fluorescence signal above a dark background. Okay, this is a general characteristic of emission spectroscopy. Okay, usually emission spectroscopy is much more sensitive than absorption. You know? The good illustration is that a stadium filled with people. You see, you now went to the ballpark, okay, and the stadium of 50,000 people are all, the seats are all what occupied. Okay, so now in the stadium there are 50,000 people, yeah, and you see it is dark. Okay, so everyone has one candle. Okay, his own candle. So there are 50,000 candles, yeah, in the stadium. Okay, okay, and then what? Absorption is what? Absorption, and now you after absorbing, now you turn off. mm, uh, for example, 500 candles. Okay, can you see the difference? Out of 50,000 candles, now you turn off 500 candles, right? That's only 1%. Okay, ordinarily it's very difficult to see whether 500 candles are turned off or not. Okay, but mm, let's assume, let's think of a different situation. Okay, it is dark. Okay, and uh, only nobody mm, has candles. Okay, but only 500 people has candles. Okay, now they lighted those 500 candles. Okay, can you see the difference? Of course, because although 500 candles are lit, yeah, it's out of nothing. Okay, so very easily you can see the difference. Okay, yeah. So usually fluorescence is more sensitive than absorption spectroscopy. Okay? Well, in absorption, we are looking for a small difference between large amount of light reaching the detector. Okay, yeah. This is general, characteristics. Okay? Water containing ppb level of colloidal lead carbonate was ejected from a capillary tube exposed to a 6 nanosecond pulse of laser. Okay, here the laser pulse, you don't need much time, only 6 nanosecond pulse, and then atomized, and then it generates fluorescence, and then it is detected by this detector. All right.